right, great. All right, time for our last but not least keynote speaker. Let's start our afternoon sessions. It's my pleasure to introduce Professor Chuchu Fan. Chuchu Fan is an assistant professor in the Department of Aeronautics and Astronautics at MIT. Before that, she was a postdoc researcher at Caltech and got her PhD from the University of Illinois, Urbana-Champaign. Chuchu is the winner of the ACM 2020 ACM Dissertation Award, and she is listed as an innovator under 35 by MIT Tech Review. Her group at MIT works on using rigorous mathematical techniques, including formal methods, machine learning, and control theory for the design, analysis, and verification of safe autonomous systems. We are so excited to have Chuchu here. So Chuchu, the floor is yours.
Thank you, Olega, and good afternoon, everyone. It's a pleasure to meet all of you here today. I'd like to share some of the research efforts we have made in the past few years on learning certifiably safe control for large-scale autonomous systems. I realize this is the second time we are talking about large-scale autonomous system. This is a traditional large-scale, like robots, quite different from Sarah's topic. So when I think about a future city that I want to live in, the first thing that would come into my mind would be the large team of robots that help us operate the city, make sure the resources are used in the effective way, and make our life a lot easier. So control theory have been developed for centuries to sort of get closer to this vision. And in the past decade, machine learning has becoming one of the driving force for the incredible development in autonomous system. So in today's talk, I want to show you that we can bring together the rigorousness in control theory and the effectiveness in machine learning to help us build large-scale autonomous system with provable guarantees on safety. So there are several challenges in making safe control scalable to challenging systems. When I started to look at large-scale autonomous system, I was very interested to know how we can handle a large number of agents. When I say a large number, it's not like 20 or 50, I mean thousands or tens of thousands of nonlinear or sometimes agile systems that we want to study. And for practical systems with high degree of freedom and under-actuated, we may have a high-dimensional state space and input space. And we may not have an accurate model of the system. That means we may not be able to find a single group of differential equations to describe everything that is going to happen for the system and the environment. There are many challenges in designing safe autonomous system in a large scale. And my talk today will focus on these three challenges. So there are many people, many researchers working on very promising approaches to tackle this problem. I'm listing here a few that are popular. By the way, this is by no means a exclusive list. It's just some popular approaches that people look at when they want to design controllers for continuous time, nonlinear, under-actuated robotic systems. So we can go all the way back to the classical optimal control to data-driven reinforcement learning. When I sort of roughly project these methods in terms of their scalability and assurance level, I would say when we use optimal control and optimization-based control using, for example, sum of squares or convex optimization, these methods, we really can trust them. We know, we have a high confidence in the results that this method tell us. But sometimes people struggle with the scalability, like how can we really deploy these kind of, oops, should I wait for the screen to come back? Okay, so, good. Okay, so I was talking that when we use the classical optimal control optimization methods, people are a little bit struggled with the scalability as the complexity of solving these problems will grow quite badly when we have a high-dimensional and large-scale system. Data-driven constrained reinforcement learning, on the other side, they have been shown to be quite effective on large-scale, highly complex critical systems. And people are looking at how to provide guarantees, how to provide assurances for this kind of method. How can we believe that they will always give us the policy that we want it to be? And model predictive control, I really love this method. It's a very intuitive implementation in the time domain to encode constrained control problem. They are relatively more scalable than optimal control, but there are certain things that we cannot prove. Like for many agents, how can we prove there's no deadlock? Everyone will reach their destination within a given amount of time. That's something that's kind of difficult to be proved using MPC, even robust MPC. So in this talk, what I'm hoping to convince you is this new technology we've been working on called neural certificate-based control can kind of break the tie and give us good scalability and high assurance level at the same time. So let's see how that is going to happen. When I talk about certificate, I mean the control certificate that we borrowed from control theory to prove desired behaviors. And I'm pretty sure a lot of you are very familiar of these different kind of control certificates. And we mainly focus on 3 types of certificate. Lyapunov function that can certify the stability of an equilibrium point. Sometimes you can also call the fixed point. Barrier function can certify the invariance of a region. If this region happens to be the safe region, we can prove safety. Contraction metric is kind of like a differentiable Lyapunov function that certifies the capability to track some trajectory instead of just a fixed point. So these three certificate functions, they share some common sort of flavor behind it. If I give you one example of using barrier function, so barrier function for a nonlinear system is just a continuously differentiable function, h, that satisfies 3 criteria. They're quite simple criteria. We want the value of this function h to be non-positive when the states are safe in some sort of safe region. And this safe region doesn't have to be convex. Actually, you can just write a classifier function to tell you which states are safe, which are not. And we want the value of the barrier function to be positive when the states are not safe. And finally, we want the derivative of h, which is the first term, plus alpha of h. Alpha is some class K function. We want to be able to find a controller. So this derivative plus alpha of h is smaller or equal to 0. That's all the 3 criteria we want. There are definitely many approaches for us to find such a barrier function h. You can manually construct it using some rules. You can use sum of squares. You can use simulation to fit some sort of function. Actually, a pretty easy way to do it, which is a very clever thing discovered by a group of researchers from UCSD back in 2019. This is a paper in NeurIPS. So they have shown that this barrier function h and the controller u together, they can both be represented as neural networks. And we can just use any standard package that you are familiar with to train for those barrier certificate and the controller with the following lost term I'm showing here. So this lost term is very easy to understand. Each of the term encode one of the criteria. We want it to be negative in safe. We want it to be positive in unsafe. We want the derivative to be negative. So what that means is we just grab 2 neural networks, or you can have one, like a single neural network that like you can split the output at the last layer. Doesn't matter. And we only sample in the state space, jointly train them using this loss term that I just defined. So it's a quite easy way of doing that. And there's actually a lot of success in terms of finding a barrier function in this way. I can show you a couple of examples. On the left here, this is how a learned barrier function looks like in a robot navigation sort of scenario. These green rectangles, they are some like obstacles you don't want the robot to collide to. And if we look at the barrier function, the green curves are barriers. So once you're inside the barrier, you're never going to get across the barrier. So you can see from here, the robots are going to be guaranteed to avoid colliding with obstacles. And these obstacles can move, it doesn't matter. It can move at some slow speed, as long as you don't throw them in front, like on top of the robot should be able to use the barrier certificate to avoid those obstacles. On the right-hand side, it's a satellite control problem. So basically, there's a satellite in the center. We want to control another satellite to orbit around it. So this other satellite we're designing a controller for, we don't want it to get outside of the bigger purple circle. We don't want to get too close to the center. So we don't want it to get inside the inner purple circle. So there's a ring defined by the two purple circles. That's the region we want the satellite to stay within, and ultimately they should come into the ring defined by the two green circles. That's the desired orbit of the satellite. If we do like this training of a barrier certificate, we can get this pretty nice result. If we look at the barrier that we learned, they pretty nicely capture the guarantees that we want to have. So I would say there's actually a lot of success in terms of learning the certificate functions, including barrier certificate, Lyapunov function, contraction metric. But is that going to solve every problem we're going to face? Unfortunately, I don't think so. Let me give you like a super simple toy example where we have four DeWings cars that are tracking some sort of path. So here, it's a DeWings car, we know it's pretty simple, but it's a nonlinear system. It's under-actuated, and they're tracking their path. Here, if we don't do any collision avoidance here, they may collide with each other. So the color of the dot will turn to blue if they are getting too close to each other or too close to the bottom. My question is, can we just find a big centralized barrier function to make sure we can have a collision-free controller? The answer is yes and no. We definitely can do it. We just put these four systems all together as a whole system, have a pretty large one piece of system, and we train a barrier function and together with the controller for each of the car, that should work. But there are several challenges in terms of using this centralized barrier function idea. The first one I would say is, first of all, even if we can do that, even if we can represent barrier functions as neural networks, it's still difficult to train those, especially when you have a pretty large system. And another difficult problem is it's hard to generalize it, right? If I train a centralized barrier function for 4 agents, now I have 8. What shall I do? Should I just train another barrier certificate function for 8? And what if these cars, they are tracking a different path? Do I need to find another barrier function? We hope not to. It doesn't seem to be the most effective way of designing a safe controller. And the second issue with this centralized idea is that if we want to design a centralized, a big barrier function, you pretty much have to have the state information of everyone, right? You have to have this big vector representing the state of every agent. So that's sort of not realistic. Ultimately, these controllers will be deployed on each of the agents. They won't have a clear picture of everyone else in this whole space. They can probably observe some of these neighbors. And the neighbor will change, right? The number, the quantity, the permutation of the neighbor will also change. So it doesn't seem like the centralized way is a good idea. Now, how can we slightly tweak the barrier function to make it work in the decentralized way? So our solution, first of all, instead of designing a centralized barrier function, we want to have a decentralized barrier certificate. As a consequence, the controller will also be decentralized. So if I put the decentralized barrier function here, you may feel like it's the same as a centralized one, except that now everything operates in a local fashion. So the input will be this pair of state X for this agent and the observation for each agent. This observation can be, for example, just a LiDAR measurement. It could be the beam array that is returned. It could be some other sensor tells you where your neighbors are when they're getting close. You can also ask your neighbor to send their location if you're within the acceptable distance. So other than that, it looks exactly the same as the centralized barrier function, but now it's fully decentralized. And we actually have a centralized barrier function. You simply take the max of all the decentralized functions. That's a global one. So you can use that if we want to show global safety, but we don't have to construct it purposely. It's just there. Once we have the decentralized ones, it's pretty easy to find a global safety certificate. Now, I don't even have to show the last term. They look the same as what I just showed in the previous slides. But I want to show you how amazing they will perform. Before that, there's another challenge. Now, observation, this vector O itself, for example, is a LiDAR input that's going to be returned by some sort of LiDAR sensor. It's going to be a time-varying observation. The length of this input and the permutation will change depending on the number of agents or the positions of your neighbors. So to deal with this problem, we just use a very neat but actually very simple trick in machine learning. This is a technique developed actually at Stanford by, it's called PointNet. So for the changing input, like a LiDAR input, we just first encode it as a fixed length vector and give that to the barrier function. So it's a quite standard trick to be used in computer vision and natural language processing, but we can use the same trick here. You can actually use any encoder that you want, but make sure that the output of the encoder is a fixed length vector. In that way, now we are not constrained to a fixed format of the input. The input can change. You can have 0 neighbor. You can have 100 neighbor. It doesn't matter. You will have there will be a fixed length vector to help you encode this input. Now with that, what will happen if we train such a decentralized barrier function? What will happen? So we will train this barrier function in an empty space with 4 agents, 4 cars randomly running all over the place. And the resulting controller, jointly learned with the decentralized barrier function, now can avoid the collision automatically. So on the right-hand side, it is exactly the decentralized barrier function and the controller that is learned on it. It's the same controller deployed on all the 4 agents. They can only see each other when they are close, but at least first of all, you don't see any blue dot. They never get too close to each other. And they kind of learn how to avoid each other. So I'm really exciting about this technology is that you can really deploy it theoretically on an arbitrary number of agents. And empirically, you can also do that. So we trained with 8 agents in an empty space, randomly running all over the places. The resulting controller is deployed on cars with the same dynamics. We can do it on 30-ish cars doing the formation control. We can do 100-ish cars following their own path. You can put it on more than thousands of cars. Each of this car here, they're running the same dynamics. They're using the same controller. And they're doing different tasks. It doesn't matter. It's exactly the same controller that is trained separately without knowing what kind of environment this is. And there is an overall safety guarantee there. You don't have to purposely construct it. It's just there to serve you. We can do the similar thing for air vehicles, like quadcopters. Actually, quadcopters are easier because it's 3D. Now the agents will have more space to avoid each other than the ground vehicle. So as long as the density of these agents stays similar to the environment you train them, they will nicely avoid each other. Of course, if you put like a lot more dense vehicle, they may not be able to. So there is some sort of a distribution you have to follow as the training environment, but it's operated in a fully decentralized way. Okay, so that is how we decentralize the barrier certificate. You can also decentralize a Lyapunov function using input to state Lyapunov function. Contraction metric doesn't really need to be decentralized. Each agent just tracks its own path. But if you wonder, what is the thing that we learned? What is the decentralized barrier function that we actually learned? If we plot this on like a top view, of ground vehicles. So on the right-hand side, it is the value of the decentralized barrier function for some agent that's not here. So at this time moment, these agents are moving. So at this time moment, you can see that the decentralized barrier certificate is pretty much the sign distance function. And this should be the thing that we learned. This is something we want to learn. So it aligns with our expectation. Turns out we can also sort of explain what is the thing that's being learned. And also there's a safety guarantee behind it that you can provide as a mathematical proof. So I want to say that I used the barrier function as one example, but actually any of the certificate functions I mentioned, the Apple function, barrier function, whether it's centralized, decentralized, contraction metric, they can be learned using a similar architecture. So we grab two neural networks and use the same loss function that's encoding the criteria you want for the certificate function and just train them. You sample in a state space. So of course, this certificate function is learned using finite number of sample. To really use it to prove desired properties, you probably want to use an external tool like a neural network reachability tool to further check that this is actually a certificate function for the entire state space. And I'm going to ignore the details here because they're separate like class of tools that we can use to do it to verify it. And this policy, we can just grab it and use in closed loop with the plant. This closed loop system will enjoy the certificate that we jointly learned. Now the difference here is when we learn a control policy, we are not using a reward function that's trying to encode some sort of good performance. We're not learning it for good performance. We are learning it so we can jointly find a proof for it, a certificate for it. And even if your system is slightly different than the one you use for training, you can use the neural certificate to monitor and adapt your system in a new environment by solving a very simple quadratic program using the neural certificate, neural barrier function, etc., to find a new controller to adapt your system to the new environment. So this is a single framework that can hopefully help you find certificate functions in a much easier way. So I have pretty much covered like the first challenge, how do we scale up to a large number of agents? There are still two problems I haven't really tackled. In the first, like in what I have presented, I have assumed that there's a nonlinear system described as x dot equal to f of xu, and we know that f. We have to know that f to be able to encode the loss term and find a certificate. But in a lot of cases, we may not know that f, right? This system, these robots you develop, they may not have like a single f to tell you what it looks like. Or in some other cases, it's so complex. It could be like a Simulink model that has blocks being connected to each other. You just don't know how to use a single f to describe it. So in the rest of the time, I'm hoping to tell you, don't worry, certificate can also be learned for these type of systems. So first of all, certificate functions can be learned for black box systems with a surrogate model that may not be accurate. So a surrogate model is some representation of the system dynamics that you find. You can sample and fit those samples in some sort of a model. It could be a neural network. It could be some other function representation that you're happy with. But it's like sort of describes some behavior of the system. It may not be exactly the same as your actual system. Your actual system, I call it a black box system. So instead of finding or learning the certificate functions directly on the surrogate model, we tell you a new architecture that you can use to find, use two different routes for the training. So if we look at the bottom, we will use your original actual black box system to generate forward simulation. So it will tell you the value of the state at next time. This is important to estimate your derivative. We need to estimate our derivative. And this is an accurate value because it's produced by your actual system. the problem is our black box system. In a lot of the cases, they are not differentiable. They are building some other tool, or they could be a physical component that's not differentiable. So we cannot backpropagate the gradient information for the training. Now, that's not an issue. We can actually use the surrogate model to propagate the gradient information back to the controller. So your controller is actually moving in the way that's sort of in the right way that the gradient tells you. So all this is possible, and it's actually very easy to implement using this function called detach function. This is already available in most of the neural network training packages that people use, like PyTorch. So detach is an identity function with zero gradient. That means that exactly describe what I just said. In forward simulation, we are using the exact state generated by your actual system for the derivative approximation. For backward propagation, we use a surrogate model. Here, the gradient information of the actual model will not be passed to the controller. We can prove, actually, we have proved in a paper that was published in RAL earlier this year that this architecture can help you find a certificate that is valid for the black box system. So, if I say that, you may not really believe in it, but let's see some experimental results in the simulation environment you saw on the first page of my slides. The left top one is our approach, and we really want to do some stress tests here. It's like a crazily dense environment. I'm pretty sure this kind of environment won't exist in real life. But we put 1,000 drones in the local area of the city and run this controller that we learned using decentralized barrier certificate. You can see that our approach is probably the only one that can nicely avoid all the collisions. We also tried this on a slightly different model of boats. So boats tend to have pretty big inertia. It's quite difficult to control them using reinforcement learning. So this video will run for a long time because you can probably see how many boats are there. Are more than 1,000 boats in this valley, but we will avoid all the collisions while the other reinforcement learning approaches will more or less fail. So if we look at more quantitative comparison result, here the first plot I want to show is we actually have pretty high sampling efficiency in the sense that with only 10% of the samples, we can achieve a nearly perfect safety rate, while the other reinforcement learning, they're pretty much stuck around 50%, 60% of safety. And you may wonder how bad, how imprecise my surrogate model could be. What if I just find, I use very few sample and get a very bad surrogate model? That's not an issue here. Even with 20% of relative error of your surrogate model compared to the actual model, we can still have almost perfect safety rate. And we can just, we can learn the barrier certificate for the surrogate model. You can see that that's the orange line. That safety rate will drop much quicker than if we use this new architecture of using black box system to generate the forward simulation and use a surrogate just for backpropagation. And we have tested in a lot of different kinds of environments on the right-hand side, including ground vehicles, air vehicles, and boats. Each of these environments have more than 1,000 agents. So here we compare still with the reinforcement learning approaches. The x-axis is the safety rate, relative safety rate. The y-axis is something that we also care about, the task completion rate. So task completion here means your agent can reach their destination within a given amount of time. You don't want them to get stuck with some local deadlock. So you can see here that our approach can achieve almost perfect in both. So that's what I'm trying to say. In the beginning of my slide, I'm trying to convince you this neural certificate-based control can really break the tie and achieve scalability and guarantee at the same time. So, so that is one. Okay, so that is like how we deal with black box system, the last missing piece of the puzzle. What if my system is so difficult that I cannot even find a surrogate model? So we are looking at an example from Air Force Research Lab. So there are a group of people from Air Force Research Lab. They developed a pretty high fidelity F-16 model in Simulink. So now you can imagine how a model looks like in Simulink. They have giant lookup tables, like they have blocks being connected to each other. You click on the block, you see more blocks, and you don't know when it's the end. This is a quite high fidelity model. And it's also a high dimensional system. It has 16-dimensional state space and 4-dimensional input space. The task is relatively easy. Just want to try to track some waypoint. That's a tiny red dot there. Now, there's a Simulink model. The issue is we cannot even find a surrogate model for it. There are 16-dimensional state space. If I'm going to sample 10 in each dimension, the amount of sample I need is just going to go beyond my workstation's capability. So we have shown that you don't have to find a surrogate model in the entire state space. We can iteratively find a surrogate model just to explore the reachable states. So let me use a inverted pendulum as an example, because 2D is easier to visualize. I cannot really visualize a 16-dimensional system. Here, inverted pendulum, we wanted to convert to the origin. Now, in each round, these orange curves are the trajectories of the current run. So at the beginning, you see the curves are all going to some other place because we don't really have a model. We just guess a model. Using that, these trajectories will lead us to explore some space. Using that, we fit a surrogate model, train a Lyapunov function in this case for tracking the waypoint, and find a controller, use that controller to generate more trajectories, collect that trajectory, do this iteratively. And ultimately, we can prove that this process can converge. Now, you don't have to use your sample to cover the entire state space. We just explore what are the reachable trajectories and use that to find your surrogate model. So that is sort of the last piece of this whole puzzle. Now we can find high certificates for high-dimensional system and for black box system. Here I want to show you the performance on this F-16 tracking. We have many more other examples, but I find this one particularly interesting. I will show you why it's interesting next slide. Here, if we look at the number of samples we need versus the reward is pretty much defined on how well you're tracking the waypoints. We use 5% of the data and converge to a perfect reward. This is the highest you can get. But the other existing approaches, reinforcement learning, imitation learning, they pretty much stay at a pretty low level. And our approach converts so fast that I have to zoom in the right-hand side on the left for you to better see how this reward changes. And if you see some of the executions of this system, using our approach, we can find a controller that tracks the goal points pretty well. There are a sequence of such points, and this aircraft is just following those. PPO will make such a funny behavior, make the aircraft spins. I don't think that's a desired behavior if you are a pilot in the F-16. Even if you're Tom Cruise in Top Gun, it probably make you throw up. We don't know why. This is always what PPO returns us. Maybe this is a faster way of getting to the goal. Adversarial inverse reinforcement learning, DRACs, they cannot reach the goal. They are always having some distance to the goal. And finally, there's another approach, SSRR. It's called learning from suboptimal demonstration using self-supervised reward regression. And they also make a spin similar to PPO, for some reason. Now, one last thing I want to briefly mention is we actually did something that's quite interesting. We insert this certificate in human behavior model. So previously, I showed you the certificate for aircrafts, for a ground vehicle, they're all vehicles. We were wondering, can we put the certificate function, like the barrier certificate, to capture the intention of colliding, of avoiding collisions in human model, while this human model is learned from real-world traffic data. So here, the setting is very similar. Each of these agents, they will have a local observation. They intend to avoid collisions, but they may not be able to. So we have to understand how well they can. And the setting is almost the same, each of the agents. Their model is from the traffic data, but they have a local observation. They have a local decentralized barrier function to help them avoid the collisions. And we have tried this on a bunch of different real-world traffic data set and compare, just insert them in the human behavior model that is learned using imitation learning. So we compare this with a PS skill. This PS skill is a technique developed by Michael a couple of years ago. So here you can see if we insert the decentralized barrier certificate, these agents that like pedestrians or cars or cyclists, they behave a lot more reasonable than the model we directly grab from like the imitation learning approach. For example, when they see a car, they won't all squeeze together. And on the right top, it's a Stanford campus. You won't see, if we just use imitation learning, the bikers will ride over the pedestrians, but those kind of behavior will not exist. It can help the car to nicely follow the rules of roundabout in terms of going everywhere, and it can also help avoid the collisions on the highway. So it turns out if we insert the decentralized barrier certificate, this agent model can generalize better, I mean in a more reasonable way to unseen scenarios. So here, it's the same intersection, but these pedestrians, when they learned, they only saw a car from the top. They never saw a car from the right. So there's a car on the right, moving, trying to get across this intersection to the left. The car is designed to be super conservative, so it will try its best to avoid any kind of a collision. We can see that if we insert barrier certificates, the pedestrians now will act in a way that's more realistic. They will try to make a way to the car if the car is not super fast. And if you make a car moving super fast, you will actually observe the collisions because even with this kind of barrier certificate, the pedestrian cannot avoid the collision. So with that, I want to end my talk with the actual simulation. I show some quantitative results, but these simulation environments are available online in our GitHub. I will show you where the GitHub repository is, but we actually can use the very similar idea, the neural certificates on large-scale autonomous system, all the way from different kind of vehicles to like manipulators. I didn't touch that, but you will use a very similar idea. So I think I'm running very close to the time limit of my talk, but this is my last slide. I have one sentence takeaway. I was hoping to show you that using the rigorousness of control theory, we can, sorry, there's a typo. We can bring the rigorousness here together with the effectiveness in data-driven machine learning to provide assurance for large-scale safe control when the systems are of high dimension and even if their models are imprecise. And everything I have talked about, all our implementation is collected in this GitHub called Certified Control. I have a QR code that can lead you to the GitHub link. That's everything I want to present today. Thank you for your patience.
All right, thanks, Chuchu, for the great talk. This one is not working. So time for one or two questions. Let's start from here.
So thank you for the interesting talk. I basically have two questions.
Mm-hmm.
The first question is a bit general. So we work on a network control system, and we are assuming that we have a homogeneous agent. So is the current result, can the current result already be used for non-homogeneous agents, or there's still some difficulties to cope with that? So because let's say we have a lot of drone flying, they may not have the same flight dynamic. This is natural. So how can we deal with that? The second question is a bit concrete. So when we are trying to train the barrier certificate and the controller, do I need to fix the structure of the certificate and the controller? So if yes, then how, in practice, what do you think is a better way to fix those structure? so that you can get those stuff easier because it's hard to find in practice. Yeah, thank you.
Sure, very good questions. The first question is about how to deal with non-homogeneous agents. Actually, in our last example, you can see like there are pedestrian models, there are cyclist model, there are car model, there are different dynamics. You have to train them separately. You have to train a neural network like for each type of agent. But they can be deployed on the same type of agent. You can train for the cars, for one type of car, and train another barrier certificate and controller for another type of car, and you can put them on the same type of cars, an arbitrary number of those. So, and in your training environment, you have to make sure they actually saw each other before. The second question, the architecture, I didn't really go to the detail of like how those neural networks look like. In our experience, they are actually pretty simple. They are normally like 2 or 3 hidden layers, fully connected multi-layer perceptron with like 60 to 100 neurons inside. So they are not large. I don't have a very good strategy in terms of picking the architecture for the neural network, but I would say you can start with something that is small and simple. Usually, if it works, it should work for the relatively small neural network. You don't really need like a super deep neural network to do it.
Thank you.
Sure.
Hi. Great talk. Thanks for the great talk. My question is, I think in the first part, related to the second question. So when you train the certificate function, I think you were training together with the safety policy.
Yeah.
I was mainly wondering, and it seemed like a very similar style to the actor critic method in the RL. I was mainly wondering, was training just the certificate function and deriving the policy from the certificate function, did that also work, or did you try it, or how does it compare between your current method?
Yeah, so the question is, can we just learn a certificate function and use certificate function online to give us a policy? So actually, that's the first thing we have tried. Unfortunately, it doesn't really work. The result is if you only train the certificate function, it is going to be very flat. So it's most likely to be a constant everywhere because a constant can satisfy those criteria. So here, what we want to find is not just like a Lyapunov function or barrier function, it's a control Lyapunov function or a control barrier function. So there, if you jointly learn them, you are finding a control Lyapunov function. You are finding at least one controller so the barrier function or the Lyapunov function hold. So that's why we jointly learn them. And it turns out we figured that you have to jointly learn them together to be able to find a reasonable control Lyapunov function or control barrier function. And only when you have a control barrier function, you can find the policy online.
So let's thank Chuchu again. Thanks a lot.